Thank you. Very excited to present this work here in Boston. First time that we organized this event here in the US. So first of all, thank you for joining. Very, very appreciate it. And also it's very important here for the community. This year we are celebrating 10 years since we made the project open source on GitHub. So it's a good opportunity to say thank you everybody used Nextflow, contributed to the code, contributed to documentation, or just use every day in their work. This is fantastic because without you, this project would not be possible. So thank you again. And also it's very fascinating thinking how this idea behind Nextflow managed to grow from a small research project into an academic institution to something much bigger. It goes beyond the project itself, the company. There is a community of people developing pipeline, using this pipeline in production every day. There is a kind of movement about this technology. So they keep together all these people together, yeah. And the idea behind the idea behind is to enable the deployment of this pipeline in a scalable and a portable manner in different infrastructure. It can be the local computer, the cloud, HPC, data center, and also to enable the collaboration for researchers, for scientists. But the ultimate goal is to allow the scientists to focus on their work. And we want to abstract away all the complexity to deploy this pipeline. GitHub repository, cloud, storage, there is a lot of things behind. And the main goal Nextflow to allow instead the scientists to focus on their job. The point that we are going forward, we are facing more and more challenges. We have more complex pipeline, more complex infrastructure, I don't know, think Kubernetes, different kind of storage. And to solve this problem, just single tool, a workflow engine like Nextflow is not enough anymore. This is why we are evolving the technology from a single tool to an ecosystem, a stack, like Eva was mentioning this morning. A stack composed by many different components, in which each component focuses on a very specific problem. You can use even independently this component, but when you use them all together, you have the best experience for your pipeline. But in this presentation, I'm going to talk a few of them, particularly Fusion, Wave, and Nextflow. Starting with Fusion. Fusion is an optimized file system for Nextflow data pipeline. The point is why we need a special file system for Nextflow data pipelines, because the real challenge for this application is not compute. You have plenty of compute, just enough having a credit card, you can buy as much as compute you want, but the real point is this pipeline consume, ingest terabyte of data, produce terabyte of data. So if you don't have an efficient strategy to manage the data transfer, I/O, into this pipeline, you are just wasting money essentially. There are plenty of different file storage, file system, but the point that most of the time they were designed for legacy system, for HPC, it does not fit very well into this context, especially in the cloud. Tend to be expensive when they are efficient, or they tend to have a very static location, and then there is an extra burden that you need to maintain to operate the service. You have to maintain the service. So ideally, we would like to avoid to have this kind of storage. Instead, use the object storage, because the object storage is the storage for cloud-native application. The point is that object storage like S3 has a mismatch with the tool that we use in data pipelines, because object storage is based on HTTP request and HTTP interface. Instead, tools into data pipelines use just the standard POSIX file interface. So the point how we can combine these two work all together. This is what Fusion aims to do, is basically an adapter layer that make it possible to use object storage like a virtual file system. So instead of having to copy the file using AWS S3 command line tool to take your input data, whatever, from the bucket, copy in the container or where you're running your tool, and then running the tool and copy back the result, what we can do with Fusion is essentially to have a virtualization of the storage, so that when you want to access a file into a bucket, you have a virtual path that is /fusion/s3, and the bucket name, etc. So, and then your tool can natively access to the data over the object storage and read and write the data from there. So there is a simplification from the implementation point of view, so that also these pipelines are portable because they don't depend anymore by specific cloud storage. But also there is a lot of optimization that can be done behind the scene to speed up the operation. This is the point of this architecture. Here there is a very basic scheme that shows how Nextflow running a data pipeline, launch the job, run very similarly into a container, and then also we operate this driver within the container. So it's not like other solution that is something in the host. Each job runs its own driver. This allows us to optimize the execution and the transfer of the data between the job and the object storage. So this becomes the adapter layer. Your job falls with the local file system. We intercept the API call, transform into S3 operation. But there is a very important point. While they're doing this interface, Fusion is able to use the compute node local stretch storage as a cache, optimize all the data operation. This is the key point of this technology. So being able to optimize data transfer using the local instance storage that ideally should be NVM or solid state disk because it's the fastest one. And also it's nice to observe that into this architecture that is perfectly distributed. They mean that all the data transferred up at the job level. So there is no a central bottleneck or central point of failure. Nextflow just uses native API to access the object storage, but at the same time, the job download the data. Each job download its own data from the object storage, upload there. So this scaled very well. And Fusion is implemented as a Fuse driver. Also, there are plenty of these other implementation out there. So you may wonder, okay, why I should use these? Well, the main reason is that because we have designed these exactly to work with Nextflow. It's not like S3FS or many other that exist already, both as open source technology or commercial software. So it's designed to work with Nextflow, work within the container, and then there is this caching mechanism that speed up all the operation. A nice thing of Fusion that also have the support for symbolic link over object storage. This seems a little thing, but have very interesting impact in the execution of Nextflow pipeline. I will show you the reason why. Finally, it's super easy to configure. We want to make it simple to operate. It was one of the main points. We don't want to operate other services. So to use this in your pipeline, you only need to add few configuration settings. The Nextflow configuration, you don't have to store anything because it's automatically added in the container of your pipeline. We want to make a benchmark to compare this technology with other implementation because we say there are many. We decided to compare their clone is a popular implementation Fuse driver for object storage. And also Amazon Mount Point that was introduced a few months ago that does something similar, but they have very different performance. We use FIO, that is a benchmarking tool for Linux, simulating different operations. Reading small files, reading big files, and writing sequential manner, random manner. When we operate in small files, like this example, 5 megabytes, they more or less have the same performance. These are megabytes per second, they measure the throughput, how fast they read the data. More or less, they have similar figure. Fusion 6,800 megabytes per second, error clone 80,900 megabytes per second, Mount Point 80,000 megabytes per second, more or less. So the fastest one here clone the Mount Point in Fusion. And more or less the same with random access. Here, what we observe, essentially, they are all very fast. But why? Essentially because behind the scene, there is the cache or operating system. And when you read this file, you are reading the file from the cache. You are not reading from S3, essentially. So this is why they are very fast in all cases. When we jump into the reading big file, we start to see a big difference. And it is a 100 megabyte file. It's very common in data pipelines. with Fusion, we can read nearly 6,000 megabytes per second. With Airclone 85, 1.3. And then still, there is a huge difference also for random access. So why there is this big difference? Because now there is not anymore the effect of the cache of the operating system, because you cannot keep 100 gigabyte file into the memory of the computer. But Fusion has this smart caching algorithm as a second level cache using the local scratch disk that speed up all the operations, something the other tools does not have. And we see also this important difference when we work writing data. So also here is very, very much faster compared to Airclone. One point even crash we didn't manage to measure. So the bottom line is that these tools were designed to work with large data. This is very common data pipeline. This is what makes the difference compared to other solutions. We want to also to benchmark executing a real pipeline to see the difference, how does it perform. And essentially here, we run NF core RNSE pipeline with a testful profile that simulates a real-world data set, running with AWS batch using S3, Amazon FSx, a shared file system into the cloud, and Fusion. So the first case is the slowest one because, okay, it's the less efficient using just S3 AWS batch. And to run all the pipeline, it took more or less 800 CPU hours. Using FSx is much faster because there is not anymore all the overhead of moving the data from the bucket to the shared file system and the result again to the bucket. So there is quite an important overhead that is only for data transferred. So the data pipeline was basically twice faster, but the interesting thing that we can do the same with Fusion. So Fusion is fast as a shared file system like FSx, essentially even a bit faster. And there is a huge difference in the cost of the execution of the pipeline. Here we are reporting the cost both for compute, data transfer, I/O operation, and the storage for 1 month to keep the result for 1 month. So with S3, the cost was $124, much more with FSx, and using Fusion, only $69. And this, apart of this cheaper, can be also a bit puzzling because we are seeing the Fusion is just an adapter on top of S3. Why? It's cheaper than S3 itself. It should be the same, no? We need to think a bit more about this. We were surprised as well. And then we realized that the effect was by the use of symbolic link over object storage. Because using symbolic link, essentially, Nextflow deduplicate all the copy of the data. Because when you run a task, and this task use the same input file, basically you are duplicating each time that you run the task, the input file. Instead, with the symbolic link, you're just moving the link to the real data. So this dramatically reduces the amount of data produced by the pipeline, so you have a smaller cost. And we wanted to also compare this effect across different execution, different pipeline, and basically we observed that when we run, we compare the execution error and seq with just S3 and Fusion, we have 19% less data produced by the pipeline, with the SCR and SEC minus 32%, ADAXEC 44% less. With SARC, this is impressive. There is a difference, 61% less data produced by the pipeline. So the bottom line is that if you are not using Fusion with Amazon batch, you are throwing away money, essentially. And availability of this technology, this support all 3 major cloud storage, AWS S3, Google Storage, Azure Blob Storage. We consider the support for S3 production ready. We are still working on Google and Azure to make to better tune the performance to be comparable with the implementation that we have for S3. You can use both with Seqera platform or Nextflow command line tool. Just adding a few configuration settings. There is nothing magic to be done. And this is a very important component about the storage. And then the other important component which we are working into this ecosystem is way component for the provisioning container for data pipelines. So container are pillar in the execution on data pipelines. Nextflow has been one of the first tools using consistently container for the deployment and to make the pipeline replicable and reproducible. The point is that in the last 10 years, changed a lot how we create container and how we write pipelines. So pipelines are much more complex. They use many more containers. There is this pattern to have one container for each task in your pipeline. So the early days was just one container with all the tools. Now we have many more containers. Maintaining all these container images is quite a lot of work. It's complicated to create, to build, to assemble, to deploy in different clouds. You have different authentication systems. So it's a lot of work. And instead, what we want to do is to remove all this work. So the core idea of way is to think container not like a static asset that is built ahead of the pipeline, but something that can be created dynamically, just in time, during the pipeline execution, so that we can optimize the container exactly for the dependencies that are needed for your task and for the platform in which you want to deploy the pipeline execution, so that you can optimize maybe for a specific CPU architecture. And also we want to make the container more declarative in the meaning that we want to say what the container should include and not how to build the container. I don't want to spend time writing the Docker file. This is ugly. And this is basically a schema of the main component. This architecture, this Nextflow running, launching the pipeline jobs using container. And then when you need to launch a container job, ask to waive the provision of a container saying, okay, this container needs this tool, use this CPU architecture, this is the user, so can use the information about the user to authenticate the access to private container, and then decide to assemble the container using Conda packages or the Spark package manager, and then send back, basically upload the container to a container registry. So essentially we implement the API or container registry, but it's not hosting images. It's just behaving like a proxy or broker, and all the images are in the registry that you specify in the configuration file of your pipeline. What's new into this project? There are plenty of new features that we implemented in the last year, what we call container threads, the support for singularity containers. There is the security discount when the images are built. There is a command line tool. But I would like to focus on 2 points. This idea of the support for multiple architecture and optimization of the container. So all the point here is to make it possible to be able to deploy the data pipelines, not just across different platforms. They can be local computer, the cloud, the HPC, but also different CPU architecture. Now there is the emergence of the ARM64 CPU architecture, so what we use in the Mac computer or maybe AWS Graviton. But to be able to use this CPU architecture that provide more cost-efficient computing capacity, you need to recreate all the pipeline, all the containers for your pipeline, because they need to be built for that CPU architecture. And when you have 100 containers, it's not so simple to rebuild all these containers when you want to run this pipeline in this CPU architecture. And so the idea here is that we can do this on demand, matching way with a package manager like Conda. This morning we'll say that this Conda is rubbish. Well, not so much. Maybe the experience is a bit disappointing when you use in the local computer. It tends to be slow. Maybe there is errors, but when you use into the cloud, like we are doing with the wave, with a stable environment, it's much better. It's very fast. So here, basically, we can deliver the container for the pipeline, depending on the CPU architecture, where just using the declaration, the Conda packages into your pipeline. And the second point is that also to make it possible to better optimize the container for a specific CPU architecture. This is why we add also the support for Spark package manager. Spark is similar to Conda, but provides an extra capability. Allows you to compile a tool, not just for a CPU family that can be Intel or ARM64, but for a very specific instruction set. So this makes it possible to even optimize the container and the tool for a very specific architecture that can be Intel Skylake, Ashwell, etc. And if you're wondering how much you can gain from this, there is this interesting research paper that shows that you can gain basically twice the performance compiling a container and the tool for a very specific instruction set compared to a generic CPU family. Okay, since there are so many things, I think it's simpler that I show in practice how does it work, this technology. And you can download the command line that I was mentioning to you before from the Wave GitHub repository. Here there are different releases. They are pre-built for Linux, Mac, and even Windows, so you can use in any computer. And I have installed here, basically, there is the Wave command line. This, when you run Wave, give you some example of what you can do, but essentially what you can do with Wave to access a container through Wave. Basically, I could just use Ubuntu. And this Wave tells you this is the name of the container that you can use with Docker on other runtime to pull, for example, the Ubuntu container using Wave. So I could do Docker pull this guy. Oops, I need to specify the name. And okay, this is nothing magic. There is no a real gain doing this instead of doing Docker pull Ubuntu, unless using Wave can be useful to authenticate the access to a private container registry using the credential for the container that you can have in the Seqera platform. So Wave basically is able to authenticate your user, authenticate also the container that the pipeline will use when you launch the Nextflow execution. But the most interesting thing is that maybe you have a container and you want to modify the container with some script or some extra content that you may need during the pipeline execution for a specific job into your pipeline execution. Let's say that you have a directory, this is my script, and here we create a script that is my script hello sh, and then I do maybe a bit bigger echo. Hello, submit, Boston. And then I say this, I give execute permission. My script, hello. Okay, now if I want to use this script within the container, sure, I build the container, the usual flow, but I can do something that's faster using wave -i for image. We said we want to use Ubuntu. And then I can specify layer to say I want to add this container a new layer, a new content that essentially is this directory that I created here. So everything that is into this directory can be made accessible to the container using this command. Then I could run this container, taking this, and then sh-c /hello to log. Let's do this. .sh. Pulling the container and then running the script into the container. So here the important thing to realize that this was not a build. The data that I specified with this command line option is added on demand while the container is pulled. So why this should be better compared to a normal build? Because imagine that in your pipeline, you have 10 different containers or 50 different containers, and all of them need a special piece of software, a script or whatever. Instead of rebuilding all of these manually or with some sophisticated CI script, we can automatically augment a new layer in the container via Nextflow using this command line tool. And this is an idea. It is exactly what we are doing with Fusion. So how we make it possible to use the Fusion file system into your pipeline without changing the container using this approach. Essentially, Fusion is appended to your container into the dynamically in this way. But yes, if you want, Wave can also build a container. I can use the usual Docker file, say from Ubuntu, I want to add the same script, hello.sh. I want to put user local bin hello.sh, and then I want to execute automatically. Okay, done. Now, how to build a container with Wave? Using Wave -f file, and then specify the Docker file. I need to specify also here, not the layer, but the context, more or less the same thing. This is always the same directory, my script. And okay, now I have again a new container name, and now Wave is building this remotely in the cloud, in the Wave cloud, the Seqera cloud. And then I can pull, like, let's do this, alias d equals docker d run this guy. And voila. And we have container B ready to run, and we can run this way. Also, we got notification when there is a build operation. This is the notification that is sent by the system. We can say the container metadata, the ID, the user, the IP, where is physically stored, some other things, the container file, the log of the build, and also the link up to a scan operation that's been done against the container to see the vulnerability. Here, there could be something that maybe we should fix. And so, basically, we can both modify dynamically container, but build container with a Docker file, but we say that if we don't want to use Docker file with container, we want to create container dynamically, not dynamically, in a declarative manner, and immediately using Conda packages or Spark packages. So how to create a Conda-based container with Wave? You can say Conda package, and you have access all the Conda collection. So here I could say I want to use BadTools 230. And we go. We have a container with BadTools, Docker run BadTools version. Pulling the container that's been built on demand and running it. And you may think, okay, this is nice, but why I should use this? Because for each Bioconda package, it exists already a Bioconda container. Well, that's true, but only for Bioconda. Conda is much bigger. There are many more channels, and does not exist container for other recipe in Conda. But above all, for one more interesting thing, with biocontainers, you have one-to-one mapping, one-to-one container. What if you want to use two tools into the same task? You don't have the container anymore. Instead, with this system, you can do Conda package and create a container with all the tools that you may need into a task. Package. Oops. It's not simple to type into this thing. Some tools, 170. And again, so basically we have another container that contains two tools. You can add all the Conda package that you want to use in this system. Docker run, this guy, some tools, version. You can do the same using Spark packages, even though we consider it still experimental. And so with this mechanism, we have much greater flexibility. This takes a bit time because now it's built in reality, the container behind the scenes. So when it's going to be ready, we start the pull, maybe. Okay, need a bit more time. Anyhow, while we wait this, another interesting thing that we can do under the built-in container with different packages or augmenting container. Oh, finally. This is Conda, this is slow. Some tools, maybe I specify something different here. Some tools. Okay, I don't know. Now I don't want to spend more time understanding why it's not giving this error. But the nice thing that apart this, okay. And what if we want to instead create a container not for Intel, but for Graviton, for ARM64. The same, I can use the same command to specify platform, Linux ARM64. Essentially, we are doing the same, but specifying a specific CPU architecture. Again, we can create a container for this CPU architecture. So now, if I run this, it should not work because this is an Intel VM. It cannot run an ARM container. And it says except format error. But this shows how simple it is to switch from one platform to another. And one thing that also was mentioned before is the idea of the Fritz container. What is Fritz container? You have noticed that every time that we run Wave, it gives us a slightly different name for the same container. If I repeat this, one more time, you see that there is this part that changes. This number represents the checksum of the container. This does not change over time. Instead, this component is a unique identity token that allows to make the container accessible for a short period of time. This is an authentication system, essentially. The problem is that using this mechanism, you can access, you don't need anymore to have the login, the container registry, but you have this name that is ephemeral, change all the time. And for some customers say, okay, but I want more predictable, stable name for the container. And this is why we introduced this idea of the Fritz container that allows to create the container with Wave and upload to your container repository in a stable manner somehow. So when you use Fritz, you have to specify the build repository, and you want to upload this in your own repository. It can be Docker. In my case, I want to use my own Wave demo. The difference now that I have a stable name. This is the name of this Wave container, and every time that I can try to re-execute, I get always the same container name because there is no change. So there is a caching behind the scene that keeps track of this. So these are the idea of the container Fritz. And another interesting thing, we said we can build container for different platforms using different packages, but also for different container runtimes. Singularity is very popular in HPC, but is used its own container file format. So if you want to build container for Singularity, it's a different experience, but with Wave, you can just say Singularity, maybe, and then we have a container that is for Singularity. If you remember, if you have used Singularity, you remember that Singularity uses not a remote container usually, but a file that is the Singularity container. So how we can use this approach with Wave is a registry. Because also Singularity, you can upload the Singularity file into OCI registry. You cannot run with Docker, but still, Singularity can pull and push from there. So exactly what is happening now. If you notice, the only difference here is that there is this prefix here that Singularity knows how to use, how to interpreter, and I can say Singularity exec, this container, and again, backtools version. So basically, now, okay, I had already cached this, so but basically, it's cached then locally, you can run like any other container. So it's super flexible. You have very many different ways to assemble provision container for different platforms, CPU architecture, container runtime, and whatever. The point is that how to use this with Nextflow. You are not expected to use the Wave command line tool. This is perfectly integrated into a Nextflow pipeline. So to use this is enough to specify that you want to use Wave into Nextflow configuration file. And we also added a new command to Nextflow to make the experience more transparent, otherwise can be a bit confusing. There is the Nextflow inspect command that allows you to inspect all the containers used into a pipeline. For example, if I type rnsec-nf, this is a small pipeline that we use for demoing, this by default use one container for all the pipeline execution. You will see they use this container that is on key, rnsec-nf 121 for all the tasks. But what if I want to use now Wave with Nextflow? It's enough that I edit my Nextflow config file, I enable wave. enable true. And then I want to use this approach, this pattern, to build the container using the conda package associated with each task into my workflow. So I say wave strategy equals conda. And this is enough to tell Nextflow to use wave, as I was showing you before. Now, if I run Nextflow inspect for this pipeline, I take this configuration file and invoke the wave service, and now I have the wave containers into my pipeline execution. I could run and use this container. What to use the freeze container? Just say wave freeze true and wave build repository docker IO wave demo. Okay, like before, I can run it again. And now it does the same, but it uses these phrased containers that are in your own container repository. Now are docker.io, Salmon for these two tasks, multi-QC for multi-QC step, and fastQC for the fastQC step. If you are not getting the link between the container and the pipeline, it's enough to just take this pipeline source code that is here, and you can go in the module, and each module declare the conda package. So we've used this declaration to decide how to assemble the container. And okay, maybe the last thing, if I want to do the same with Singularity, you may have Singularity enable. Singularity is complicated, this word. Enable into your pipeline. And when I run the same thing, I have the same container built for Singularity. And okay, so these are the main capability on this on wave container provisioning service. So change a bit the way the flexibility that we have to assemble the container in our data pipeline. And we are making this available as a version 1.0. We are operating for more than 1 year, and the last year served more than 1 million containers requests, so we consider stable enough to go in production. Also, a very nice thing that we are also making available as an open source software, so other the command line, also the wave backend is accessible in this GitHub repository. You can go there, download, play with it, modify the code, make contribution if you want. Also for people that are interested to use on-prem, we are also making available as an enterprise distribution starting from next year. So there are many different ways you can use this software. Okay, and then the last part, Nextflow. Nextflow is the pillar of this technology, this stack. The last year, all the work now, but part of the work was focused to smooth the interoperability across the stack. So between Wave and Fusion was the main theme, is the main theme of the version 23.10 that we make available the past month. So not surprisingly, now we have the support into Nextflow also for Spark Package Manager for the reason that I was mentioning before. Now there is a new directive that is Spark that you can use like somehow conda to declare the dependencies for the task into your pipeline. And again, this can be used to build the tool locally or using Wave. Along the same manner, we add also the support for the architecture directive. Now into your pipeline task, you specify your architecture and also the microarchitecture like this. And this is used mainly by Spark in conjunction with Wave to target very specific CPU architecture when you want to run your pipeline. Then also, Fusion is first-class support file system into Nextflow pipeline. It's supported by the cloud executor, AWS Batch, Azure Batch, Google Batch, but also other executors like Kubernetes. And this also, especially with Kubernetes, Fusion simplify a lot the deployment Nextflow pipeline into this cluster. You can even use Fusion with local executor. So you can run your pipeline in your computer, use S3 as the scratch word there for the pipeline. This is maybe is not super efficient, but makes sense maybe if you use EC2 virtual machine to scale the pipeline vertically. If you launch a solid virtual machine, you can use just single node scale in this manner without caring about the local ABS disk. Finally, there is also the support for Fusion for Swarm, LSF, a Green Engine bash scheduler. It is also open an interesting chapter because allow to use the distributed file system, or this virtual file system on top of object storage with HPC bash scheduler. And of course, here make more sense not to use cloud storage, maybe unless we are using a parallel cluster that was showed this morning. But if you are operating Swarm or another is HPC on-prem, you can use a S3-like object storage, like manual or Ceph, to move all the scratch or the pipeline into the object storage. I think this is a very interesting solution. Few small things that are new instead, not into the 2310 release, but the latest Edge release of this month, 2311, with the support for Singularity OCI mode. Again, container, we say the container are important. Now Singularity has a new feature, the ability to run natively Docker container. So it's not needed anymore to convert a Docker container to the Singularity image format, can run directly. And to support this, you need to add a configuration option into the Nextflow configuration file. And this is, I think, very interesting because reduce the need to create container specifically for Singularity, so increase the interoperability of container for our pipelines. Another nice addition that we adding to Nextflow, what we call topic channels. If you have used Nextflow, you may remember there are mainly two types of channels, what we call value channel. This is a kind of channel, essentially you can associate a single value, and then the other task can only read that value. And then we have the queue channel that is one point-to-point communication channel for one task that produces some data is sent to another task. Now we are adding a new type of channel that is topic that is more like a broadcasting system. So the idea is that you have a shared channel to which many tasks can write and many tasks can read. This can be useful to implement some specific pattern. The main reason came from the NF core pipeline in which there is this need to collect the version on each tool, and there was this continuous concatenation of channel over channel over channel to create a big channel containing the data coming from all the processes. This can be solved instead in a much more elegant manner using this idea of the topic, where many processes like this, now there are only two here, but basically this is showing that I have an output, the tool version I send over the topic version, and another task, or more than two, can do the same. Always, this file is sent over the same topic. And at some point, your pipeline, you can reference the topic by the name, and can be used like any other channel with an operator or into a process to collect all the data came from these processes. And another extension that we are adding to Nextflow, what we call the command output type. This is always somehow related to this problem that there is in the NF core pipeline to collect always the version of the tool in each process. If you notice that there is always this boilerplate at the end, the bottom of the task, that is needed essentially to run the tool with the version to capture this metadata, and then it's sent out like I was telling you before. And this is doable, but it's a bit ugly because I have a lot of noise into this task. I would like to see only the real command into this task. So instead of doing this, what we can do now, the upcoming version, is declare the command that they want to execute like a new type, that is CMD. This run on the fly, the command, capture the output, and then we can use like we were doing before. And okay, quick overview roadmap for next year. There are really a lot of things on which we are working on, but I would like to focus on what we call for DSL3. DSL3 is not going to be a new version of Nextflow or the language, but it's more the idea, not the idea, the need to have a better experience for Nextflow developer. The overall idea is to have a static type language instead of a dynamic typed language like it is now, that make very difficult to have a proper error reporting system or to be able to detect syntax error into the pipeline execution. You can discover this only during the pipeline execution. Instead, we want to make this experience much more static oriented so that the Nextflow, when you launch a compiler pipeline, the parser can identify all the problem and provide much better error reporting, and also having a much better ID experience. So while you are typing your pipeline code in VS Code or maybe IntelliJ, the environment can automatically suggest, okay, you can do this, you can use this operator, maybe can highlight the error, and so on. So they're planning to have much better developer experience writing the code for Nextflow pipeline. That's it. I hope that you enjoyed this presentation, the idea of Nextflow. It is the idea to evolve Nextflow from a workflow engine to an ecosystem of different component tools, always keeping the original vision in mind, so to make it possible to remove all the complexity and to allow the scientists to focus on their work. Thanks a lot for your attention. Also, a few seconds to say thank you all the fantastic team working into this project. Thanks again.